So we have talked about the time evolution of the wave function, how the wave function evolves with time as time progresses, and which we have seen that it can be obtained by solving the time dependent equation. And for a simple systems, which means for that when the Hamiltonian is independent of time, then the time dependence of the wave function is obtained as exponential minus I e t by h cross. And we have seen some examples for that. Okay. Uh, just to remind you that these wave functions are vectors. Okay. So these are like column vectors which has elements. If you write it in position basis, then suppose you're talking about the positions of the particle to be R1, R2, R3, R4, etc. Then this wave function written in the position basis will have elements of the vector to be having values at R1, at R2, at R3, and so on and so forth. Okay. Now, coming to another question related to this is that what is the time evolution of an operator? Now, operators, we have seen that operators are matrices, okay, and we have calculated expectation values of operators, and we know that when the expectation value, say for example, of the Hamiltonian matrix are the energy eigenvalues for the problem. Okay. Now, how do we take a or rather consider the time evolution of an operator? Okay. So, we have an operator O, okay, at time t equal to 0, and how do we get the operator at time t equal to t, some time, okay. You can simply write it as that operator, and you can remove the sign as well, 0, and how do you evolve it to a time t. So, that is a question that we are going to address and this question is important because we have seen the expectation values of operators and so on. So, whether the wave function of course evolves, so whether the operators evolve as well and how do they evolve, that is the question that we want to ask and answer. And again, without going too much into the derivations of this question or the answer that leads to this, sort of the answer to this question is, I'll give you the final answer to this question, that how operators evolve with time, and it is the answer is given by the equation of motion, which let's call it as EOM in short, for operators. So that way you can consider the Schrodinger equation to be an equation of motion, the time dependent Schrodinger equation to be an equation of motion for the wave function. Now we want to know what is the equation of motion for operators, and I'll finally just give you the final answer to this. The derivation is a little involved, not suitable for this level. So this is any operator, let's call it as O. You can put a small tilde on top of that or a hat on top of that, but it's not required. We know that O is an operator, which it can be any operator. Say for example, the angular momentum operator, okay, which you have seen in the rotational mechanics, that gives you the equation of motion. Okay, so it's like dl dt. Okay, so we have a IH cross here, and this is equal to the operator O and its commutation with the Hamiltonian of the system, and the inherent assumption is that neither the operator nor the Hamiltonian are explicit functions of time. So, they do not have explicitly time as a variable entering into their expressions, but you want to see how, as the time progresses, how these operators actually evolve, because the wave functions evolve, okay, and because the wave functions evolve, these should also have an evolution as the time passes by, okay. So, as I said, O is any operator, could be angular momentum, could be momentum, linear momentum, that is, or could be position. So, let me give you an example for this and it will lead to something very similar for you. So, let us write it here, okay, or let us also make another partition, okay. So, we have a generic form of the potential, the Hamiltonian, to be of the form which is p square over 2m plus v of x. We have said this several times, that this is the kinetic energy, and p square has a form which is minus h cross squared d2 dx2. V of x is the potential. We have taken them for solving Schrodinger equation, this to be a constant because we wanted to stick to simpler situations, but in principle it can be a function of x. It could also be a function of time, but those are more complicated situations and we do not wish to address them. So, let us see that how we want to get the equation of motion for two quantities which are x and p. I have told this earlier that x is an operator, okay, which when acts on a wave function or a state, it gives the position of the particle corresponding to that state. So, this is an operator. If you wish, you write it with a small hat on top. P is of course an operator which we know that has an eigenvalue of h cross k for a state which is a plane wave state. Say for example, we can give a just a small example here, that this is a form of P and this acts on a state. It gives you the eigenvalue for that state corresponding, I mean the momentum eigenvalue for that state, and we'll just fill it up here and returns back the state itself. Okay, this is called as an eigenvalue equation, which is what we have learned. Now, if the state corresponds to a plane wave state, so we'll replace this by a plane wave state. So, this is a plane wave state is exponential ikx. Maybe there is a normalization which we are not worried about because the normalization will cancel from all sides, and this is exponential ikx and so on, or you can take it as a minus ikx, just to have I mean there is no problem in taking it as plus ikx also. So, when you take a derivative with respect to x, you get a minus I or you can take it as plus ikx, okay. Let us see, it does not matter. So, it is minus ikx ih cross and I k exponential ikx, and this, if you simplify, this comes out as h cross k exponential ikx. So, here this will go and sit here, okay. So, that is the eigenvalue of the momentum operator when it acts on a plane wave state, okay. So, these are operators. So, let us see the simplest example of the evolution of the x operator and the p operator, okay. And because these are the variables, or these are the operators that you generally deal with, okay. So, I write down I h cross. So, first for x, okay, the position, this is, we are going to do it first. So, it is dx dt, this is equal to x h, okay. Now, this is a commutation relation. So, what's a commutation relation? Once again, to remind you that AB commutation is equal to AB minus BA. Okay. So, in general, for normal, numbers, this would have been 0. 5 into 7 is nothing but 7 into 5. So, if you take a subtraction between them, it will definitely give you 0. But these are not numbers, they are operators, and the order in which they operate on a wave function matters, and that is why this is not 0 in general. It could be 0 for some particular problem, but not in general. So, how do we calculate x and h? So, x has the h has two terms, which are p square over 2m, and there is a v of x. Okay. Now, you see, if v is purely a function of x, this operator is going to commute with vx, because suppose v of x is like x square, then x and x square, which is the case for a harmonic oscillator, x square is equal to 0, because this is like x cube and this is like x cube again. Okay, if it's purely a function of x, then of course this doesn't survive. So we can neglect this, but we cannot neglect p square over 2m for the simple reason that x and p do not commute, which is what we know. Now, if you want to calculate this, let me do that here. I will use a relation, commutation relation, which is between three operators A, B, C. Okay, and this is B, A, C, and plus A, B, C. Okay, that's the formula. You can easily check this formula. It's not a problem. So I have two operators P and P. Okay, so B, C both are P and P. So this can be written as X P P. That 2m I am going to take into account maybe once and for all. Okay, that 1 over 2m there. And then there is a X P, sorry, this P should have come according to that formula. You should write first outside on the left, and then this, and then this. Okay, that's the formula. Do not, so this is a third bracket. Let's put it a curly one. So it's actually a bracket, and these are commutator brackets. Okay, so this is equal to 1 over 2m, and this is IH cross, you know. So this is IH cross P and plus a IH cross P, because this is also IH cross, and then multiplied by P, and this is equal to, so there are two IH cross and there's a 2. So this is like H cross P over M, and that's the time evolution of this. Sorry, I forgot some IH cross. Yeah, IH cross P over M. There are two of them, and that 2 cancels with this 2 in the denominator, and so this is equal to IH cross, and then you have a dx dt, which is equal to a IH cross P over M, and this cancels out, and so dx dt is equal to P over M. This is a very sort of known relation to you in classical mechanics, in Newtonian mechanics, and what you have to do is that simply you have to take a expectation of the operator in order to have a correspondence with classical physics. So this is equal to d dt of expectation x is equal to expectation P by M. So that's your very analogous to the Newton's law, or the definition of its dx dt equal to velocity. So that's the thing that you have seen in classical mechanics. Okay. So that's one, and I would expect that you do it for P, but it could be a little tricky. So let me do that for you as well. So I'll do that for P as well. So I H cross dP dt. P is not such a simple operator. P is a differential operator. Okay, so you have to keep that in mind. So this is equal to PH cross, sorry, not H cross, H, the Hamiltonian. Okay, PH. So again, go back here, your H is equal to P square by 2m. So P is definitely going to commute with P square by 2m, right? Because that's a quadratic in P. So I don't need to consider the first term. I'll only consider V of x, because if V is a function of x, that P and x are not going to commute with each other. Okay. So this is a P and a Vx. Okay, and the way one can do it is one can actually write down in order to calculate. So let's go back to that thing. So let's write a dp dt, which we have said at the end of this step. So this is equal to a 1 by h cross, and then there is an expectation of this. So I can take the expectation, which is the average value, like this, okay, and replace P by minus I H cross ddx, okay. So that's the, these are the two things that you're going to see. And when I take an expectation, what I do? So I take it between the basis states some psi, okay. So some psi is there, whether you write it or not. When you put an angular bracket, you should keep in mind that there are these psi's that are going to appear there. So this is equal to 1 over I H cross, and this is like your the first one is a psi, and then so there's a I so I H cross, so a minus I H cross ddx of Vx, and then operating it on psi, and the second term will be a minus psi, this is a Vx operating on ddx, so there's a minus IH cross ddx. So I'll have to write it minus IH cross and a ddx acting on psi. Okay, so let me erase this x from here. ddx of psi. Okay. Now you see this is a ddx, vx and psi x. Okay. So this you have to operate it twice. Once keeping vx to be constant, operate it on psi x, and then another time when you keep psi x to be constant and operate it on vx. So that can be done. If you are comfortable, then let me erase this part of the calculation which you have already seen. So this is equal to 1 by I H cross, and then there is a psi, this first term. So this is equal to V of x minus I H cross d psi dx. Okay, and then I've kept Vx constant and then taken a derivative here, and then I'll take a derivative with plus psi, taking this the psi of x, and then taking a derivative with respect to so this will be like minus I H cross dV dx, okay, which you can write it as gradient of V, and which will be identified as the force there. Okay. Now so this is there, and so on. Now you see that this V of x, so this looks like the first term and then there is a term which is minus of psi v of x and then minus IH cross d psi dx, which is the this term, the second term in the original expression. These two will cancel out, and you are going to have, I mean, you can put this thing there, and what you are going to have is this term, this I minus IH cross. So this becomes a quantity, okay, which is dv dx and so on. So let's put this angular bracket here, which this will of course give me equal to 1, and this IH cross etc. will cancel, and what we get is that so your dp dt ddt of p, which is equal to so this p expectation is expectation value of dv dx or del v del x, whatever you want to call it. Okay, so this is the and if you identify this as ddt of because your this one your dx dt came out as this, your ddt, let me move to this part of the board, because you have calculated this x is equal to p over m, okay, and then you have just now calculated it ddt of p is equal to minus dv dx, okay. Then what you can do is that you can take a double derivative of equation 1 so that you can eliminate one of them. So taking I mean double derivative means one more with respect to t, okay, that's what I meant. So it's d2 dt2 x is equal to ddt of p over m. So that's your equation of motion, and this is very familiar for you because your dp dt is equal to nothing but minus dv dx, and that's exactly analogous to Newton's law that you have d2 dt2 of the expectation value of x, which is a number, okay, or which is a scalar variable because you have taken the expectation value, and that's equal to the force, the negative gradient of the force. I mean the negative, so this is equal to force because force is defined as the negative gradient of the potential, okay. So this is how the time evolution of operators are considered, and they are calculated, and you do this again for the harmonic oscillator problem where this v of x that we have written there, so your h was p square over 2m plus a half m omega square x square in the tutorial, okay. This is what I wanted to point out, that in addition to the wave function, we also have the time evolution is applicable to the operators as well, any operator, and that needs to be calculated by calculating a commutation relation. See, this is important. Then whether you take an expectation value or not, that is not important. Here we have taken the expectation value because it was coming to be very similar to what we have already seen in the context of classical mechanics, and that's how the expectation value comes. But otherwise, this is the equation that you need to keep in mind, and as I said, the derivation is involved, which I avoided, but the rest of the things, the application of this is should be understood, and this is called as Heisenberg's equation of motion, okay. Let me write that somewhere. It's equation of motion, and we need to put a Heisenberg's equation of motion or Heisenberg equation of motion, okay. So this is all, and we'll see the applications for oscillators.